Okay, so here continuing with our class 8 motion, okay, science. These questions we're going to cover, you can write it down, okay. And then the question we're going to discuss first today is what is reference point, okay, in motion. So let us take an example. Like we said in the last class, when we follow the inductive approach of learning, that is moving from a familiar example and easy example to the definition, we find it easier, okay. So let us do that even today. Position of a village is 2 kilometers north of a railway station or of the railway station. Let us say here there is, for example, a tourist is coming to a village to visit a village for the first time. So he won't know where the village is, right? So in order to get this village, he asks a local person the location of the village, and the local person tells him maybe over phone, right? While he's coming to the village, that it is 2 kilometers to the railway station. The train will bring you to the railway station, so that is a familiar location. You will know when you reach. So from there you turn 2 kilometers to the north. So what the local guide is doing is, he is using the railway station to point the tourist to the village he wants to go to. So that point that he's using, railway station, with the help of which he's trying to give direction to the tourist, is called the reference point here. So here the reference point is the railway station, right? So that is the meaning of reference point. So once we get it in terms of a simple example like this, let us now try to define together. You write along with me, okay? So the point, okay, the point to which, okay, the point to which the position of an object, the position of an object, okay, the point to which the position of an object or even a location is referred to, okay, is referred to. Why? So that it will give meaning to the position of that object, okay. The reference point will give meaning to that object that we're going to discuss, right? The point to which the position of an object is referred to is called reference point, okay, reference point. So that's the first term that we're going to learn as we start the chapter motion, okay. It's going to be important. Next question number 2, okay, what is motion? So we are now coming to the main topic of the chapter, okay, motion. Give an example or write an example. So here we will start again with the example because that's easier, as we said. So let us take an example of motion. Let us say a moving car, okay, a moving car with respect to a stationary tree. To a stationary means not moving, stationary tree on the roadside. Write it down. Okay, this is an example of motion. So let us discuss this a little bit. Now let us say this is a car that is approaching a tree. That is moving on the road and approaching a tree on the roadside. So as time goes by, let us say this is 0 seconds. At 1 second, he would be here, the car. So as the time goes by, after 2 seconds, he'll come nearer to the tree. So the car is changing, the distance between the tree on the roadside and the car is changing as time goes by, right? That is an example of motion. Okay, so let us now, keeping that in mind, which is a very simple example. So if we see a car is beginning to change its position with respect to another stationary object, then we say that the car is in motion, right? So after 2 seconds, the car, let us say in the beginning at 0 seconds, the distance between the tree on the roadside and the car is 10 meters. After 2 seconds, it's 8 meters. After 3 seconds, it is 5 meters. So the distance between the tree and the car is changing with time. So that is an example of the car in motion. So let us say here, an object, or we can also say a body, okay? An object or a body, whatever. Any one of these two is enough actually. An object or body is said to be in motion, if its position, okay, if its position changes, okay, the key word here is changes, with respect to its surroundings, okay, with time, means as time goes by, the position of the object changes with its surrounding, okay, then the body is said to be in motion. Now, having done that, let us discuss the opposite of motion. Next question. We're going to do these questions 1, 2, 3, 4, 5. So let us go to question number 3. Cite an example of rest. Cite and write it down. Example of rest. So rest is going to be an opposite of motion. Then after that, define rest. So we're following the inductive approach again, because we find that it's always easier to take an example that is familiar to all of us and then move to the unfamiliar technical definition of rest or motion, etc. Right? So if you follow that same thing in your personal self-study, you will find it easier. Okay, just a suggestion that might really help you. Okay, so next year, let us say example first. So a stationary car, this time not moving car, here we took moving car, a stationary car with respect to, okay, a stationary car with respect to a tree on the roadside. You know that the tree never moves, so it's already stationary even if you don't mention. A stationary car with respect to a tree on the roadside is an example of a body in rest. So we get this very clearly, right? This is just a simple case of, like, for example, in the morning 9 o'clock you saw a car parked on the roadside and it is 5 meters away from the tree on the roadside. Then at 10 o'clock, after 1 hour, you come back. It is exactly in the same position, and the distance between the reference point, the tree, and the car is still the same. So it has not changed its position with respect to the reference point, the tree. So that is an example of rest. Okay, so let us try to define it. So just in the same way you've defined here, an object is said to be in rest, okay, if its position does not change, so it will be the opposite of motion, does not change with respect to its surroundings, okay, does not change with respect to its surroundings with time, comma, with time. Even if time progresses, the position is not changing with time. I hope you're getting it, right? So that is your question number 2, or 1, 2, 3, sorry. Now we'll go to question number 4. Let us write it down. You can pause the video and write it down if you want. If you have already written, then just follow the video, okay? Next year. Question number 4. Let us write the question first together. Citing examples first. Citing means giving, okay? Citing examples. Citing means mentioning, actually. Same thing. Citing examples first Okay, citing examples first. Define the following terms. So we have to define some important terms in motion. Define the following terms. Let us see what terms they are. Okay, the first one, let us put it as A. Magnitude of a physical quantity. What is magnitude? We're going to discuss that. Then B is distance. Okay, distance. And then C is going to be displacement. So let us see these three terms today. Okay, now in order to do this, let us start with the example again. Okay, so our answer. Now your example again, because that way we're finding it easier, right? Next here, let us say there is a swimming pool here. This is the swimming pool. Starting point is 0 meter, then 1 meter, 2 meter, 3 meter, 4 meter, and then 5 meter. So this is a 5 meter long pool. A simple case, everyone of us can understand, right? So let us say there is a boy called Rocco, okay, in your class, who is going to swim across this swimming pool in this manner. So let us say his starting position is A. So Rocco is here. His starting position is A. So this is his starting position, is called initial point or initial position in your textbook. Okay, so from here he swam and reached B, let us say. And when he reached B, he didn't stop there. He turned back and came back 2 meters here. So his final position is here, let us say, C. So this is his final point that he reached. That is the journey path of Rocco as he swam across the pool and came back towards the middle of the pool and stopped. So let us take this example now here. Now let me take here B first. Distance example here. So write down distance. Here, distance covered. Actual distance. Okay, let's just do like this. Here, actual path length covered, okay, by Rocco here, okay, is called distance. So we are taking in terms of example here. So tell me, what is this? That is, the distance that he covered is how much? Can you tell me? Actual path length means from here to here he traveled, so there will be AB. Then not only that, he came back 2 meters here to here BC. So that will give you how much? Let us try together. Yes, AB. Yes, that's good. 5 meter plus BC is 1 meter, 2 meters. So the distance covered is 7 meter, right? So that is the meaning of distance, okay? The actual path length covered by an object. Okay, next here, let us go to C then. So the shortest distance between the initial and final position or point, whatever you can use, position of a body or object, of a body, in this case a moving body like Rocco swimming across the pool, okay? Position of a body is called displacement. So in this term, what would be the displacement of Rocco? So that is, displacement will be equal to what? His initial position is A. He started from here, we know that. and he came here C, went to B but came back to C, means the shortest distance between A and C final point is not AB plus BC. It is this shortest path between the two of them. So there will be AC. So displacement will be AC, which will be equal to, let us try, 1 meter, 2 meter, 3 meter. So this will be only 3 meter. So in this case, we can clearly see that distance and displacement are not even the same value, 7 meter and 3 meter, because their definition is also different. Because displacement is the shortest distance between the initial and the final position of an object or body, okay? Or it can, yeah, so that is the difference, basic difference between distance and displacement. I hope you're getting it. And finally, A, what is magnitude? So the numerical, you can write it down, numerical value of any physical quantity or a physical quantity is called its magnitude. So magnitude is simply the numerical value of a physical quantity. Physical quantity means terms like displacement, distance, all these are called physical quantities. Displacement, distance, force, like yesterday we discussed, height of a boy, all those are physical quantities, okay? So here, example, you can say numerical value of distance covered by Rocco is how much? Distance covered, numerical value is 7 meters. So this 7 meter is called the magnitude, and displacement is only 3 meter. So magnitude means the number value here, 7 meter and 7 and 3, right? So that is the difference between distance and displacement. Finally, one more question for this class, question number 5. Let us go and do that. Important that we get this very clearly. So question number 5. Question number 5 on your text, question 9, okay? That is, differentiate between distance and displacement. Differentiate between distance and displacement. So we're going to discuss in detail these two terms again in this question, even though we have known the basic difference between these two, right? So let us divide our notebook into right hand and left side with a line, middle line, and write here the distance on the left side, and then maybe displacement on the right side. And let us see the difference, basic difference between these things here. Number 1, okay? We have already known, so we can just write down 1. The actual path length, the real path length or the actual path length, okay, moved or covered. You can just use the same, okay, moved by an object, okay, object irrespective of direction. So we do not take the consideration of direction because this is a scalar quantity, okay? Distance we know is a scalar quantity. Irrespective of direction is called distance, okay? It's called distance. Like in the case of Rocco swimming, he went to the end of the pool but came back 2 meters, so 5 meter length of the pool plus 2 meter. And we didn't consider he's moving back plus minus. No, it's the actual distance covered. That's why it is not dependent on direction, right? And here, the shortest, okay, the shortest path length or distance, you can say the shortest distance or path length between the, okay, between the initial position, between the initial and final position, okay, final position or point also you can say, position of an object, is called displacement. So remember, displacement is the shortest distance between the initial and the final position of a moving object. Okay, point number 2 difference would be, okay, here write down first. For point number 2 and 3 we'll just do some activity down here. Okay, so point number 2 would be, okay, let us write down here, so we need space down. Point number 2 is distance is always positive. Okay, let's just write it down first. Distance is always positive. And number 2 here, displacement, okay, displacement may be positive or negative, may be positive or negative. Not only that, or it can also be 0. It can be 3 things: positive, negative, 0. We'll see soon why. Let's write the third point also, so we can club these two together and take example to make ourselves understand. Okay, distance is a scalar quantity. It is a scalar quantity because it does not depend on direction. Here, number 3, it is a vector quantity. Now let us see what this means here. Now let us take here below your what you have written. You can write on your notebook, write along with me. Okay, so here let us say case 1. Case 1 is rock swimming again. Let us say from here 0.1 meter, 2 meter, 3 meter, 4 meter and 5 meter. Let us say 5 meter pool again. Let us take the same example as we took a moment ago. Okay, so he started from here, let us say, and he ended here. Initial point, I'll just use short abbreviation form. Okay, and this is the final point. So his distance will be how much? Distance, let us use small short d. If he stopped here, that his distance is 5 meter, right? This is the first case. Then displacement, we'll just write displ. Okay, displacement is so d1 and then displacement 1, first case, let us say. Please write along with me. This will make you understand these 2 points very clearly. Okay, it is a scalar quantity. Now, okay, so here displacement is the shortest distance between the initial and final point. So this is the same now, AB, which is again 5 meter. So this is the first case. Now let us take case 2, and case 2 is again like this. Let us say 0. Okay, and then, okay, let us make it shorter so we have spaces. 1 meter, 2 meter, 3 meter, 4 meter and 5 meter, let us say. Again, his starting position is this one, initial point, and then his final point is here, let us say. He reached B, and then his final point, okay, he reached here, let us say. This is his final position or initial final point, whatever. So here the set of answer will be what? The set of answer will be, let's make it space we need, so let us write here. D1 is 5 meter and displacement 1 is also 5 meter. This is case 1. Then here D2, distance covered in this case, case 2. This is case 2, let us say. He went from here to here, AB 5 meter, plus came back here, so 2 meter. So it will be 7 meter. I hope you're getting it, right? And his displacement, let us say 2, will be the distance between the initial position and final point C, not B. So this will be the short distance AC, which is 1, 2, 3. So this is 3 meter. Okay, and then let us take here a case again, case 3. Here his initial position, here A, 0 meter, 1, 2, 3, 4 and 5, let us say. Meter, meter, meter. Same swimming pool. So he swam here and reached here. Okay, he reached here. And then he came back right here to the initial position. So here A is the initial position, IP, initial point. Then he came back right to A again. So C is final point. So you can notice that A and C are in the same position. So this will be D3. Will be, he went from here to here and came back here, means 5 meter went and 5 meter come back, means 10 meter is the distance covered, because it is the actual path length. Then displacement, his displacement will be distance, shortest distance between initial and final point. So initial point A, final point also same, so there is no gap, they are overlapping, coinciding. So displacement in this case is 0, there is no value for it in this case. Now let us take here case 4, and case 4 is, let us say here 0, 1, 2, 3 and 4 and 5, let us say. This is his initial position, let us say. And then, so this is the initial position of Rocco. He went here, covered 5 meter, came back here. And then this time, let us say there is some space even behind the initial point of the pool. There's water area. 1 meter back he went, swimming 1 meter back. He went here. So his final position is here. He went here B and finally came here C. So final point is C. Final point is C. So this is the final point. So final point and initial point are quite near, but they are not overlapping this time. So distance covered D3 will be what in this case? He went from here to here, 5 meter, came back here, 5 meter, right? So 10 and 1 more meter back, so 11 meter he actual distance covered. That is the distance. Then his displacement will be, this is 4, I think, sorry, 4. The 4, case 4. This is case 4. So D4, displacement. So 4 possibilities are there. So displacement 4 will be what? Distance initial point A, final point C. So the distance is 1. But it's on the left side of the initial point. So this time it will be, right side is +1, +2, but left side, you know, like your graph only, this is now -1. So we can see that displacement is negative here. So these 4 cases are possible. Case 1, 2, 3, and 4. With that, we will explain this. Distance is always positive. Let us see whether it's true or not here. Case 1, +5 distance. Case 2, +7. Case 3, +10. Case 4, +11. Always positive. So that is correct. Now let us read this. Yes. Displacement may be positive. Let us check. Displacement +5. Yeah, it is possible to be displacement to be plus. Here also plus. Right? But not only that, it can also be negative. Let us see any displacement negative. Yes. In the case of case 4, where he swam beyond the starting point, to the left of starting point, it was -1. So this is correct. Positive, yes, it's possible. Negative, displacement can be negative. Or displacement can also be 0. Like in case 3, he swam from here to B and came back to the initial point A. The final point C is also with A now. In that case, displacement was 0. There was no displacement. So yes, displacement can be 0. We have seen this, right? Now, here distance is a scalar quantity, because we don't take into consideration the direction. The total distance is like right or left. It is always going to be actual path length. So it does not depend on direction. So it's a scalar quantity. But vector is, displacement is a vector quantity, because once it changes to the other side of the initial point, it can also become minus. So direction is involved here, right? So it is the shortest distance between initial and final position. It is not the actual path length. So the direction is going to be very important. That's why displacement is a vector quantity. One more point, the fourth point, okay, write it down, and these cases will explain it to us. In a given situation, distance is always greater, okay? In a given situation, distance is always greater, okay, it can be greater or equal to displacement, or equal to displacement. Distance is always either greater or at least equal to displacement, never lesser than displacement. Okay, so in magnitude, displacement in value, numerical value, magnitude. Let us see the examples and see whether this is true or not. Distance always greater or at least equal to displacement, never lesser than displacement. Case 1, here, displacement, distance 5 meter, displacement 5 meter, equal, you see. It can be equal, see, at least equal. That's case 2, distance is 7 meter, displacement is 3 meter. Again, this now it's greater than displacement. Here, distance 10 meter, case 3, greater than displacement 0. And case 4, distance 11 meter, displacement -1, definitely greater than displacement. So you understood, right? It is always greater, distance is always greater or equal to displacement, but cannot be less than displacement, okay? Number 4, the fourth point here. In a given situation, okay, in a given situation, displacement is always smaller, so it will be just the opposite of this one. Displacement is always smaller, or it can also be sometimes equal to distance, but it cannot be in magnitude, but it cannot be greater than distance, okay? So if you have understood this, I think this one no need to explain, right? So compare these cases with this last point, number 2 and 4. These cases will explain point 2 and 4 very clearly to us. Okay, so that concludes this class. Okay.